So I'll give you guys a chance to get, a couple seconds to get set up yet. Or are we loaded and ready to go? Okay. So OCE for S1 asks you to read those graphs. Now, for the first part there, this is questions 1, 2, and 3 that I'm kind of looking at here right now. They have this graph of smartphones versus non-smartphones. And what they did for each bar is they put the smartphones on bottom and then they stacked the non-smartphones on top of them like that. And I wanted to look at question 2, where it asks, is it easier to read the sales trends for the smartphones or the non-smartphones? Did you guys give an answer to that? Yep, the stacked bar graph for numbers 1 through, it's actually numbers 1 through 5, but I'm just looking at 1 through 3 right now. So in problem number 2, is it easier to read the sales trends for smartphones or non-smartphones in this chart? The smartphones, and why? Okay. Yep, it gives you, the bars are darker, so they're easier to see. The other thing that for me is easier is I look through that bar graph. Can you tell me, is there a period where the actual, from one quarter to the next, where the number of smartphones sold went down? I see 2 or 3 spots actually where it happened. Yeah, from fourth quarter 2007 to the first quarter of 2008, that was a decrease. Looks like, where did you find another one? Perfect. Fourth quarter 2011 to the first quarter of 2012 was a decrease. There's one other really small one that I see. It's another fourth quarter, 2013 going into the first quarter of 2014. Now, there's a very good reason for that. If you look at them, that one not so much, but all the other ones, the fourth quarter sales seem to be a high point. Can anybody tell me any reason why sales of phones would tend to go up in the fourth quarter of a year? Okay, there's a lot of sales on. They're getting rid of the old phones and the new phones are coming out, or the new phones have just come out. So everybody's got to get the new model. There's another big reason in the fourth quarter. It's coming up here in about 4 weeks. Christmas. All retail sales go up in November, December, in the fourth quarter of a year. So there's almost always that natural drop off in January in the first quarter of the next year because of that large sales for Christmas time. So that would explain why all those drops are fourth quarters. Or fourth quarters going into the first quarter of the next year. Now, the more difficult task is, can you tell me, just by looking at the graph, can you tell me when the sales of smartphones or non-smartphones, they tended to decrease? So can you tell me from one period to the next, one where they actually increased? So So an increase in non-smartphones. That's really tough to see on the graph, isn't it? Why was it so easy to see when the smartphones decreased, but so difficult to tell when the non-smartphones increased? Well, what advantage? Oops, go ahead. Perfect. That's exactly what I was looking for there, Sam. All the smartphones are on the bottom. They start at 0. They have a flat bottom to them. So all we have to do is look at where the top of the bar is. Because the top of the bar compares to the top of any other bar for smartphones. Since the non-smartphones are stacked on top of them, we can't just look at the top of the bar. We actually have to subtract the top of the bar and the bottom of the bar to get the number of non-smartphones. So this is a case where, would it have been, can you think of a way to display this data that would have made it easier to read both of them? So that it still would have been easy to read the number of smartphones, but would have made it way easier to read the number of non-smartphones. There you go. That side-by-side double bar graph where you have smartphones and non-smartphones side by side like this. And then the height of the bars themselves would still be 2 different colors, but then the heights of the bars would be comparable. The stacked bar graph here is used to kind of make that point. They didn't necessarily get real specific about it here, but that was the purpose of having that on there, was to show you that those stacked bar graphs are difficult to read. If we did it as a side-by-side double bar graph like this, it's a lot easier to read. Did anybody have any other questions on 1 through 5 of the OCE? Okay, then I want to jump. Oops, go ahead. If you had the data in Excel, it wouldn't be too bad to convert it. You would end up, here, let me grab Excel here and pull it up. And of course, there are a lot of other programs that do this graphing. There's Minitab and other things out there that, like Minitab is a little bit more statistically accurate than Excel, but I'm just going to do A and B as 2 things being compared together. And we're going to do some rough data here for it. We'll go 2002 to 2009. Okay, so there's our data. Let's do a quick graph here, see what we can come up with. So let's do the column chart. So this is the stacked chart. Now I've got to format my data series and get rid of okay, that's not it. Select data, there I go. I want to get rid of the year as a variable. The year is not a variable. So there's my stacked bar chart. Okay, horizontal, that's what I want here. Get rid of those. I'm going to actually select my data labels. There. Now let's see if that works out right. No, it's not liking something I did there. So we'll just go back. So anyway, here's our stacked bar chart. If I wanted to change this to a side-by-side double bar graph, all you have to do is go change series chart type, change chart, and there click, that's not what I want, double bar graph. Here we go, bar graph, column graph's what I want. And there I can click side by side, and there it is. So that's all you really have to do in Excel is just do a change chart or chart type, change series chart type, I should say. And you can change that from stack to a double bar graph really quickly like that. Now, the biggest thing in this problem is we weren't given the table of data. So without that table of data, we would have had to have gone some work reading the graph, trying to find the numbers to put into that table in order to make that work. Okay, so jumping up to questions 6, 7, and 8, the homeless shelter question here. They want to create a graph, actually number 8, they want you to create a graph to display that data. So we have kids, adults with families, and then single adults. What type of a graph do you think would be best for displaying that kind of data? So take a graph of your choice. Well, whenever we have a category, we want to break it down into pieces of that group. What's the good type of graph to show that? Well, let's look at it from a little bit different point of view here. If we had a total, which we do here, let's say we're looking at you guys, looking at your degree. If you're doing a bachelor's degree, you have 120, it's 120 to 128 credits total. So let's hit it with just 120 credits. And let's say out of those 120 credits, you are required to have 16 credits of math, 12 credits of some sort of English or communications. You're required to have 40 credits within your major. And you are required to, let's say you're required to have 8 credits of literature. And see where we're sitting at there, 60, 76. Oh, let's say you're required to have 16 credits of history and 28 elective credits. If I wanted to break down the credits within your degree, what type of graph would be the best way to show what portion of your degree is each type of credit? Perfect. A pie chart or a circle graph. So the way we would display it on there, of course, is usually by a percent. We have the 120 credits total. We would find what percent each of these are. So like for your major, that's 40 out of 120, which is 0.33 or 33%. That's 1/3 of your credits is your major. You might keep going, like 28 for your electives. 28 divided by 120 is 0.233. Just under 25% are your electives. So you can see very quickly on that graph that electives are just under 1/4 of your degree, and your major credits are exactly 1/3 of your degree. And if we put more of them on there, you would see that relationship build. There you have your English and literature and all that. So yes, that would be the best graph to show something like that would be a circle graph. Okay, that's really all I wanted to point out on the OCE. Did anybody have any questions on those? Okay. So then starting in S2 here. In S2, we're looking a little bit more into more types of graphs and some quirks with those graphs. And what we're going to start out talking about is we're actually starting about college math class. We're looking at a college algebra class. And success rates in college algebra. So what I'd like you guys to do is I'm going to give you about 6 or 7 minutes here. I want you to read through that situation, problem situation, the tracking student success in college algebra. So read through that problem situation, and I would like you to look through questions 1 through 3. We'll give you a few minutes to discuss them together and work on those questions, get answers down for them, and then we'll talk about them, like I said, about 6 or 7 minutes. So for the graph they gave here, student success in college algebra, we can see, again, I'm going to do this just kind of roughly. It goes from 2010 all the way up to 2016. And what we see is we start out at about 75% in 2010. In 2011, we moved to a 72%. 2012, we jumped back up to a 74%. And then 70, 2013, and so on. Now, as we look at this, what's that? As we look at this, it's easy to say that, it's easy to conclude that these percentages are dropping rapidly. But if you look at it really closely, it's really only dropped from 75% to 64%, which is still a significant drop. But why does it look like it dropped so much here? What's going on the axis over here that makes it look like there's such a big difference? Well, they're close together, but also when this axis was numbered, where do we usually start the axis when we number up the side of a graph? At 0, and here they didn't. And we talked about this before with those bar graphs. If you have a bar graph, you can't necessarily look at that and say that the bar X is twice as big as bar Y until you look at the scale. I mean, this might be 100, 101, 102, and 103. Oops, I forgot to pull that out for us today, but that's okay. So anyway, yeah, looking at here, it looks like bar X is more than twice as big as bar Y, but it isn't because the scale starts at 100. And the same thing here. It looks like this is a huge failure here compared to what it was here. It looks like it's actually like 1/6 or 1/7 the pass rate that it used to be because the graph doesn't start out at 0. Now for even with that in place here, is there a trend that appears to be occurring here? By trend, you guys understand what we're asking by trend? By trend, what we're saying is, can we say that the scores are consistently going down or consistently going up? Looking at this graph, can you say that there's a trend? Well, it does kind of look like, yeah. Yeah, it looks like it goes down and then it goes up a little bit, then down and up. However, it does look like the drops are a little bit bigger than the rises. It does look like it does go down a little bit, but I'm going to challenge you with this. If I took this last one off of here, now does it look like it's going down or up or anything? Maybe a little bit, right? But not as significant. Having that last one on there that was really small tends to make your mind really think, oh my, this is really falling fast, doesn't it? So then the next one, part 3, question 3, is asking, what questions would you ask if you were looking at this data, trying to decide if this was a significant trend that we needed to do something about? What questions would you ask of this person who compiled the data and made the graph so that you could get a better understanding of what's going on? What information do you think you would still need to know? Did you guys come up with any questions? There are actually a lot of questions. Oops, go ahead. Okay. There are actually a lot of questions kind of hidden in this problem. It takes a little bit of time to maybe dig out. One question I would ask is, what is a success? Is success defined as completing the course with a C? Is it defined as getting a D minus or better? Did they get a certain percentage? How was a success defined? That would make a difference on how I felt about this data. I might ask, how many students are in each class? Maybe these classes up here had a large number of students in it, and this class right here might have been a really small class, so only having a couple of students fail might have really brought the number down. I might ask, when was the class? In other words, what semester? If this one right here happened to be the first time we ever offered the class in summer semester, I don't know if you guys have taken any summer classes or not, but the pass rate in summer tends to be a little bit lower because it's shrunk down to 8 weeks instead of 16 weeks. So they have to get through the material faster. So we do tend to lose more students. So if these were all, and you pointed out that trend, Sam, that tends to go up and then down. If this were like fall and spring students, fall students, spring students, fall and spring, that might explain why students who start in the fall maybe do a little bit better than students who start in the spring or take the class in the spring. But then if this were a summer section over here, would go a long way to explaining why that really dropped far at that point. Can you think of any other questions you might want to ask? What year? Okay, yes. What year in college? Was there a change? Did they change it to where students were taking it before in their junior or senior year, and now they're taking it in their freshman or sophomore year, or something like that? That may have changed, what they're doing. So yeah, what year in college those students are is a big deal. Did they change textbook? Changing the textbook might cause the grades to fall, or other curriculum changes. Now here's the one, go ahead. There you go, grading. Did the test versus homework change? Might even ask, professor, did it change from one professor to the other? Maybe that's why it goes up one semester and down the next, is one professor teaches it in the fall, another professor teaches it in the spring. And maybe one is a little bit more of a difficult grader than the others. A little bit different. Some of them I would ask test scores coming in. Maybe the test scores, the ability level of math coming in is getting lower. So is there a correlation between their math scores on the entrance tests and the percentage of students who are successful in that course? Okay, do you guys have Excel on your computers there? You do not? Okay. Well, then you can either use Excel or you can sketch it out by hand. What I'd like you to do is I'd like you to sketch this graph, starting the y-axis at 0. So we're going to have to go up to about 75. So I'm going to give you just a couple minutes to fill in this graph, sketching it out with that axis going from 0 to 75 instead of 62 to 75. So as you sketch this out, of course, we had 75 here in 2010. See, 72 in 2011, 74 in 2012, down to 70 in 2013, 73 in 2014, 71 in 2015, and down to 62 in 2016. Now, as we look at it displayed that way, does it look like there's anything to worry about? No, it looks pretty flat there, doesn't it? So the dilemma, and this is where statistics and dealing with data involves way more ethics than people think. Is there an ethical way to display this data? Is one way better than the other? And that question is hard to say. I would say that definitely this graph might not show the differences as well as it should, because if you were looking at this graph and I asked you 2015, what is the value? Well, I try to trace this back. That's really tough to get an exact value because the numbers are so close together. Whereas on that other graph, the graph that we were given, well, 2015 is right there. I mean, I can get that to be exactly 71. So I can get an exact number off of that graph. But this graph, the first graph, definitely exaggerated the differences from one year to another. So where is the most ethical display of that data? That part's hard to say. I guess the biggest thing in statistics is the phrase is your own best interest. Which is kind of a fancy phrase for say what's best for you or what are you trying to do. If I am trying to say that, let's say I am arguing that math success is falling and that we need to do something about it. We need to change our math curriculum, or maybe we need to start making students take a placement test and making them take a prerequisite math course before they do the college algebra or whatever. If that's what I'm trying to argue, if I am trying to claim that the success is getting smaller every year, of course, I would want to use this one because it shows it looks more like they're falling. But that's the one that supports my claim the most. In statistics, when we talk about statistical ethics, we tend to go, the ethical thing to do, if there's two different displays that might elicit different responses, the most ethical way to do it is what is in the least supportive of your own best interest. So if I am trying to claim that success is falling, the most ethical graph for me to use would be this one right here. If I were trying to make the opposite claim, if I were trying to claim that success is staying fairly close to the same, then the most ethical graph to use would be this one, because this one is against the one that's most easily, that someone else could look at and most easily see the points against my argument. So that's where it's weird in statistics. If we're trying to make an argument, we must highlight the evidence that could possibly be used against us so that other people can look at it and make their decision based off of that. Not too many other places where that's the ethical thing to do is the thing that is worse for you. I mean, definitely not in politics, right? That's what drives me nuts every time I see an election campaign, because they're of course using a lot of statistics, but they are stretching them and bending them in their own best interest, which is so hugely against ethics in statistics. Like I said, in statistics, it's to display them in the way that least supports your own best interest, or that would most support the opposite side of the argument so people can look at it. And if they decide to agree with you, it's because the evidence is so overwhelming that even given that worst possible display, they still decide that you are correct. That's also a precursor, by the way, for those of you that do take statistics, you get into hypothesis testing. That is kind of the basis of all that decision making. If we get into statistical decisions, what we tend to do when we do statistical decision making is, let's say that there is something we are trying to support, or a claim that has been made, or that we are trying to show. We assume the opposition is true. Like if someone claims that, graduation rate in Wisconsin high schools is less than 80%. And I claim they're wrong. Let's say I think they're wrong. That claim is wrong. What I have to do is I have to assume that their claim is true. And then I have to gather evidence that is so strong that I can't stick to that assumption, that nobody else can stick to that assumption. So you present evidence to other people to trying to show that it's true, but because if it really is not true, then the ability to gather evidence to support it is so tough that we must assume that it's wrong. I know that's kind of a double talk there, but that's how things kind of work in statistics. We assume the opposite and try to show it's true, but then the evidence stacks up against it to the point where it can't be. Okay, it's 11:19. We're a minute early for our break. Let's go ahead and take a break. Let's do about 10 minutes. Let's come back at 11:29 and we'll go on with the next section here in S2. Issues with my pen today. My batteries are going dead in my pen, so it shuts off after a few seconds. I did get your test yesterday, Sam. I haven't had time to grade it yet because it came in as I was leaving yesterday. So I will have that graded this afternoon, and then I should have all the grades posted tomorrow morning. I'll get the curve figured out tomorrow morning, and I'll have your test then sent back to you all tomorrow morning so that you'll know exactly where you're sitting. Make sure you go through and look in Blackboard. The grades in Blackboard should be updated then. I will make sure as I post the test scores and curve those scores and change them in Blackboard that all the homework scores are updated as well. So if you're looking at that and your homework score doesn't look that good, let me know. That just means I haven't got your homework assignments from those sections yet. So hopefully, once I give you the tests back, if there are any questions on the test, hopefully we'll have a little time next Monday that we can go over them. I haven't looked too close at what my plan for S3 is yet, but we should have a little time for it. And I'll make sure I look over the final assessment here soon, so give you a little bit of an idea what's on that. Okay. So our next section we want to look at here, we're looking at considering percentage, actual values, and population size. And this actually is working back with this data here from the college algebra class. We have those percents. I'm actually going to make a little table here so it's easier for us to see them. And let's put in those percents here as percents of success. We had 75%, 72, and 74. Let's see, we had 70, 73. And we had 71 and 64%. So year and success rate. So now let's say that we find out that the class size that this is taken from is one class of 40 students each year. So what that means is each year 75%. How do we find 75% of 40? Perfect. Well, 40 times 0.75 is 30. So that would mean 30 out of 40 passed the class. Now, how about for 72%? Well, 40 times 0.72 would be 28.8. So I'm going to have you guys go down quick and fill in the rest of these numbers. 74, all the other percents, and find how many out of 40 that would be for each semester. That's 29.6. As we go down through here, are we seeing much of a difference? Well, if we look at this, we're getting numbers like, 75% was 30 out of 40, 72% was 28.8, 29.6, 28, 29.2, 28.4. Well, that certainly isn't much of a change, is it? Now, the last one, the 64%, 40 times 0.64 is going to be a little bit smaller, 25.6 out of 40. So you can see there is if we're only looking at 40 students or so, the changes in those percents are literally less than 1 or 2 students each. The other side of that is, what if we are told that this data is taken from the whole college, which has 200 students per semester enrolled in the course? Well, now, if that's the case, 75% of 200, 200 times 0.75 is 150 out of 200 that pass. The 72%, 200 times 0.72, that's 144 out of 200 that pass. That's a difference of 6. Still not terribly large difference. So again, I'm going to have you go through and fill in those numbers, figure out each percent out of 200 students. Now, if we look at that, if we look at those numbers, again, the first several years, it didn't look like a big deal. We had 150, 144, 148, 140. It's changing by, 6 or 8 students per year. But now that 2016 dropping to 128, that's 14 students less. That's a huge drop. Now that starts to look a little bit more significant. So we talked a lot about sample size last week in our one day there before Thanksgiving on how sample size is an important thing. If we're only looking at one class of 40 students, while dropping from the mid 70s down to 64% is only a couple of students difference. But if we're looking at the whole college and all the students enrolled in all the sections of that course, if it's out of 200 students, now that's a lot of students, a lot more students that are not being successful. That looks like it might be more significant to look at. Okay, so moving on then, the next type of plot we're going to look at is one of our most basic plots for data, but also one of our most telling plots, and it's called a dot plot. And the way a dot plot works is it's really just a number line. I don't know why that angle's up, but it's the way it's going to be, I guess. Well, here, my preaching about statistical accuracy, I'll try to make it flat. There we go. Still has a little bit of a slope to it, but we'll deal with it. Let's say I want to look at scores on, I just had a test in my business math class. So let's look at scores in my business math class. So I'm going to make a number line that should have been bigger, apparently. That has to encompass the whole range of scores that students had on that test. Let's say that nobody had over a 95 on that test, just because my number line ran out. So what I'm going to do on a dot plot is I'm actually going to plot the scores of the students had on those tests. So I have 24 students in that class. I'm going to have to plot those 24 scores. So let's say the first test I graded had an 81. So I put a dot at the 81. Let's say the next test had a 74. So I put a dot at 74. The next one was a 79. I put a dot there. Next one was a 63. I may have had a 88, an 82, 67. And I keep putting these dots on here. Now, let's say I had a 46, which was actually my low score on that test. A 92. Now, if I get another 79, there's already a dot at 79, so I put a dot above it. Say a 76, 84, 87. Let's say we got another 81, and then an 80, 71, 59. Now, in reality, when you're grading a test, because questions tend to be worth, 2, 3, 4 points each, there are certain numbers that are more likely to come out. Like if there's 25 questions on the test, obviously 96 would be 1 wrong and 92 would be 2 wrong and so on. So those scores tend to be a little more concentrated because of practical reasons. But we're going to keep plotting scores here. So what do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 17. So I need 7 more to get my 24. Let's say I've got a 74, another 76, another 79, another 81, 69, another 87, an 80, an 82, and let's say we get another 81. Now, looking at that, it doesn't really tell us a whole lot about the shape of the data. Part of that is there's only 24 points there. 24 scores seems like a lot, but it really isn't when we look at displaying data. So let's say I'm going to go back the last 3 years. I teach that class every semester, so over 3 years there's going to be 6 classes. So there's going to be a lot more data points. And as I put them on my dot plot, some things become way more apparent to us. Now what we see going on here is what we refer to as a data distribution. We can see here that this data tends to have kind of a curve here. It's called a bell curve. When they talk about curving scores, this is what they're talking about doing, is taking those data points and turning it into a bell curve. As we talk about measures, calculating means and ranges and stuff like that, what we're doing, we're not really describing the individual points that we have. What we're doing is we're describing the shape of that curve that kind of traces over the top of those points. And the number of points we use is very important. Like we said, 24 test scores sounded like a lot. Well, if you're trying to really get a good shape of the data, it's not. Here, I probably have somewhere around 60 or 70 scores on there, and even that could be better. Okay, so now in section 2 here, where it says be wary of inexact terms. So we're going to start with question 7. The following 2 dot plots show hypothetical course grades. So what we have here is there's a dot plot for a class of 40 students in 2015 and a dot plot for a class of 40 students in 2016. What I want you to do for question 7, I want you to answer parts A, B, and C. Read through those and looking at those dot plots and answer those questions. And again, I'll give you about 6 or 7 minutes and we'll talk about your answers that you got for those questions. Okay, so question 7A asks us, if success is 80% or higher, what percent were successful in each of those graphs, each of those plots? So if we look at 2015, if you look at that dot plot and you count the number that are 80% or higher, how many were at 80% or higher? So if you looked at 80 and counted the dots above it and then to the right of it, how many did you come up with? That's okay. For the plot for number 7, if we define 80% or higher to be a success, for the 2015, for the grades of 40 students in 2015, how many of those students had a score of 80% or higher on that dot plot? 28. So 28 out of 40 gives us what percent? You got it. That is 70%, which is the exact, very comparable to the number they gave us before. I believe it was 71 for 2015. For 2016, if we look at that dot plot, how many of them are 80 or above? 26. Good. So if we do 26 divided by 40, we get 0.65 or 65%. Very good. And in the plot, it was 64 is what was given before. So we can tell by looking at these dot plots that the success, 80% or better is not exactly what they were considering a success, but it's close to it. Now, what if we define success as receiving 74% or better, which is part B? Now, I'm not sure if in this institution 80% is a C and 74% is the bottom of the D's. I'm not sure why they chose those percents, but I would assume that there's significance there in the grading. But for 2015, how many of those students had a 74% or better? 38. So 38 out of 40 would be what percent? 95%. For 2016, how many of those students had 74% or better? 38 again. So of course that will also be 95%. So again, I'm not totally sure what the significance of those percents are, but if we assume that they had a significance to the grading, let's say that 80% or higher was a C or better, and that 74% or higher is a D minus or better. What this is showing us is there's still 95% that are passing the course. If a D minus is passed, now the C or better dropping from 70 to 65% isn't a huge drop, but maybe it is something to be worried about. So when we were doing our linear models, if you recall, we did an equation like, y equals 200 plus 35x. I always define, x is, years after 2006 or whatever our first year was. I know it seems a little tedious to define stuff like that, but this exercise here shows just how important it is to define what we mean. By changing the way we define success, we could greatly change the percents that were displayed in this data. Whether we define success as getting a C or define success as getting at least a D minus, it greatly changes how we look at this data. I think pretty much any of us would accept a 5% failure rate if it's a 95% success rate. Now, of course, there are some things that might affect why we would choose a C or better compared to a D minus. At WITC, if you get a D minus in a course, if there is a next course that is a prerequisite for, you cannot go on to that next course. At WITC, you have to have that C or better to move on to the next course. Unless you test out, yes. Good point. Yeah, you got to keep me in mind. I see that. It is. I tend to wander. If that's the case, where college algebra in many schools has at least one class after it, usually most schools require a sequence of college algebra and then at least statistics, or if you're in engineering or something like that, your next step would be into a calculus series. A D minus might not be a success. So there's practical things that come into how we define success as well. And the biggest thing is we've got to make sure anytime we report numbers like success rates that we are very explicit in explaining what those numbers mean. What is a success? How many students were in our group? Did we just do this one instructor's class, or did we do all the students in that class in the whole school? About how many students were in that class? Things like that made a big difference. I know for us, one of the things that would make a big difference, we have a math with business applications course. I'm just going to call it business math. I teach one section of it. It's at night. Usually Wednesday nights. It's actually tonight that I teach it from 5:30 till 8:30. That's over ITV as well. Business math is offered, since we brought it up, as ITV. It is offered online. And it is offered in the classroom, face-to-face. And we have found through the years that face-to-face, and I'm just throwing numbers out here, I don't have exact numbers, the pass rate might be around 88%. Online, the pass rate is significantly lower, like 74%. ITV, that rate is about 84%. But if we break it up even further, face-to-face is all in the classroom with you. Online is all at a far site at a computer tuning in, so there's no division there. But ITV, you can have students in the classroom with you, or you can have students that are over the network. And for that course, every section we teach, there are some students in the classroom with you and some students over the network. And let's say the success rate of students that are in the class is 86%, and students that are over the network is 81%. So you can see here by looking at those divisions, that 84% was very accurate, but it wasn't being in an ITV style class that made students less successful. It was where they were at in the class. You can see the students in the classroom were very comparable to a face-to-face class, which would make sense. They're in the classroom. They are basically face-to-face. The ones over the network had a significantly lower success rate. So those that are arguing that ITV is a good mode of delivery for courses, because 84% success compared to 88%, it's almost the same as the face-to-face success rate. Well, that would be a good comparison that would tend to make evidence in favor of ITV being a good mode of delivery. Or by breaking it down, saying the students that are over the network only have an 81% success rate, which is significantly lower than the face-to-face success rate. So now here's the question. If my goal is I want to increase ITV offerings, which way should I present the data? Should I present the data as everything grouped together, or should I present the data with the ITV split apart? Now, before you answer that, I want to do this ethically. So ethically, which way should I present the data? If I want to increase the number of ITV offerings, should I present it with ITV altogether or ITV split apart? Remember that phrase, against your own best interest. Very good. I want to increase the offerings. Ethically, I have that ethical obligation to show the strongest evidence against what I want to do. And having them split apart shows the strongest evidence against using ITV classes. So that would be the data that I should show, because that makes ITV classes look the worst. So I should show that data to whoever I'm making the argument to so they can make their decision based off of it. If I just want results, and I don't care about ethics, which way would I show it? Ethically, I'd show them split. If I just want to convince people of stuff and get my way, I would show them together, right? Unfortunately, that tends to be the political model. I usually have a field day during election year when I teach statistics, because when there's time in a classroom class especially, there's usually time to go through and look at political advertisements and just pick apart the statistics. Because it's weird, because we looked at this whole defining success and how it really changed those percents. I've seen it happen where, okay, let's say state A, we're not going to name a particular state here. Within 5 minutes, you'll see one advertisement that said, State A led the region in job growth in whatever year. And 5 minutes later, you see an advertisement from the opposing candidate that says, State A was among the worst in the nation in job creation. Well, looking at these, they seem to contradict each other. If one is saying that the state led the region in job growth and the other is saying one of the worst in the nation in job creation, how can they both be true? Well, first of all, you'll notice this is taking it out of the region. But what is the region? Maybe the region is the 3-state area that you're in, and the other 2 states in the region were the only 2 states in the nation that were worse than your state. That would put you among the worst in the nation. Other little things is, how do you define job growth? You define job growth as total earnings, total earned income in the state, or do you define it as unemployment rate? Do you define it by hours worked, total working hours? Do you define it by only new jobs? Now, by new jobs, how do you define new jobs? There's several definitions of that. New jobs could be recalling laid off workers. If workers were laid off 6 months ago and conditions in the state changed so they can be recalled and back to work, are those counted as new jobs, or are those counted as old jobs that are just active again? Or does it have to be fields that were not formerly in the state? Let's say fields new to the state. So you can see there's a lot of different ways of defining these things to skew those statistics. Anybody have any questions? Okay, so remember that for Thursday, OCE for P1 is due, and PNL for P2 is also due. And then to work on for next Monday, which will actually be due on Tuesday, is the OCE for, I put P there, that should be S. I don't know why I put P in there. S1 and S2. The OCE for S2, work on for Monday, and the P&L for S3 for Monday. Anybody have any questions? Okay, that's all I have for today, so I'll let you out of here a few minutes early. Like I said, I should have your test, the last of the tests graded this evening. I should have the curve all figured out and posted for you tomorrow morning, and I'll have the test back to you tomorrow morning. You bet. You guys have a great day. Thanks.